installation. So these are the content or point that we are discussing majorly. So what we discussed so far, that what is the current that a person can withstand, or what is the tolerable current for the person, and whether the AC voltage or DC voltage, which one is dangerous and for the person. So regarding this we discuss, taking the reference of IEEE 80, that what is recommended in the IEEE 80 regarding the dangerous to the person, and how much current a person can withstand. So the IEEE 80 clause 6.1 is telling that any person with around 50 kg can carry 116 milliampere for 1 second, and if the duration is reduced like 0.1 second, so the same person can withstand 367 milliampere current. Whereas if the person weight is 70 kg, in that case the tolerable limit would be higher than a 50 kg person. So these are things we have discussed in the previous classes of the earthing. After that we discussed that what is the earthing, and since equipment is placed on the foundation, and foundation we are making on the ground level, so equipment is already placed on the earth. So why additional earthing we are talking? So what is the earthing? So that we have discussed, and the definition of the earthing that we have discussed, and why earthing is required for the equipment, and if earthing is not done, so what could be the case, how it could be dangerous for the equipment and the person. So that we have discussed, and then we discussed that not even the equipment which is live, even the equipment which is placed in a store for the backup purpose, those equipment should be connected with the earth as well. And we take the example of the transformer and the DC. So mainly these two equipment connected with the earth if they are placed for the future backup purpose, because these equipment contains the oil, so there could be case of the static discharge. So that all concept we have discussed in the earlier classes of the earthing, right? So sphere transformer earthing, and then we discuss about the drawback of the ungrounded neutral. So type of the earthing system we discuss. So we discuss that mainly we have the two type of the earthing. One could be one is the equipment earthing, and another is the system earthing. So system earthing we do for the equipment self protection, and equipment earthing we do for the human protection, not for the equipment protection. There is a like contradictory in the definition. Equipment earthing used for the human protection, whereas system earthing used for the equipment self protection. So far we have discussed about the system earthing, right? So far we have discussed about the system earthing in the detail. What is the system earthing and how we do the system earthing? What is the way of the system earthing? So that all we have discussed. And equipment earthing we have discussed about a power plant. In a 20 megawatt power plant we have considered, and for that equipment earthing we have discussed. And now we will take the case of the substation, and for that we will discuss about the equipment earthing. So here we discuss system earthing type, that what is the type of the system earthing, and after that we discuss that as we use the NGR in the system earthing. So where we use the NGR, where it is required and where it is not required. So these are things we discussed. And then we took the example that if in case we have any electrical installation and we have a transformer, and that transformer is feeding connected to the bus, and that bus is connected to any motor, in that case the transformer neutral must have the NGR. So this concept we discuss, and we discuss the few example from the project, right? So these are the concept regarding the earthing that we have discussed. Difference between earthing and grounding. So the NGR calculations, and then NGT, why we use the NGT, and then type of the NGT, and after that we discuss that how the NGT we connect into the drawing and how it appears in the drawing. And after that we uh, we have considered zigzag transformer, their connection and their sizing rating calculations. right? So and after that we discuss about the, so these are the regarding the earthing transformer calculations, and thereafter we discuss about the parallel electrode or earthing pit we make. So what should be the minimum gap between the two earthing pit, or what we should maintain, and why we should maintain that. So these we discuss, and then we discuss about the equipment. So these are the system earthing. So after that we come on the equipment earthing, and equipment earthing we discuss that the electrical installation could be two types. The first type, it could be any industrial electrical installation. So for that we discuss about the earthing equipment earthing arrangement in the last Sunday class, right? The equipment earthing, and
Yes,
how
sir.
we do the equipment earthing for any power plant, industrial electrical power plant. So that we have discussed that how the earthing layout we prepare, and then what is the calculations we do, and what is the, like these are the calculations that we perform, and what the input required, right? So these are we have discussed for the industrial electrical earthing, and we took a reference of a 20 megawatt thermal power plant for the calculation reference. And now we are coming for the electrical substation or switchyard type earthing calculations. So we are taking any substation or switchyard type electrical installation, and for that we will discuss now the earthing calculations. And before the earthing calculations, we will discuss about the earthing arrangement as well, right? I hope so. Any query from the previous classes regarding the earthing? If no, so we can proceed with the substation earthing calculations. And this is very much important for the interview point of view, and this is a kind of the major drawing and calculations we have to perform in case of the substation. So please focus what we are going to discuss. This is extremely important with respect to the switchyard or with respect to the substation, right? So this is going to be a very important class for the earthing. So any query from the previous? If no, let me know. We can proceed with the substation earthing.
You can proceed, sir.
Okay, we can proceed. Earthing is equipment earthing. Yeah, equipment earthing. Yes. Yeah. Okay. Okay. So the substation or switchyard equipment earthing. How we do this earthing arrangement. So before coming to the calculations, the ultimate agenda for me is to discuss the calculations which I have here, here. So this is the calculation total document that we prepared. So revision sheet, then general arithmetic design calculation for 132 by 30 kV substation per patch, and then basic design basis references, and then the abbreviations, and then finally the calculation. So ultimate target for me to discuss this earthing calculation sheet. But before coming directly to the earthing calculation sheet and telling you the values that we need to put here, before that we should understand overall concept. And once we know the overall concept, then this earthing calculation sheet would be too much easy. So what value we are putting, why that value we are putting. So we should have the entire knowledge that why those value we are putting, and why this value we are putting here, what is the reference of those values, and why we are following this kind of the steps, why we are following this kind of the step. So a to z I'm trying to discuss about the substation. So before coming to this earthing calculation Excel sheet, we'll discuss about the overall basic concept. Then we'll come on this earthing calculation sheet. And for the earthing calculations, as like you all know that we follow the IEEE 80. This is the universal global standard. Everywhere in the world it is followed. So IEEE Guide for Safety in AC Substation, IEEE Standard 80. 2000 is the revision. Latest revision is I think 2013. So main standard is the IEEE study standard
Sir,
80.
it is common for GIS and AS both.
Yes, it is common for the GIS and AIS both. IEEE Guide for Safety in AC Substation. They are not telling the AIS substation. They are telling AC substation grounding. That could be GIS, that could be AIS, that could be indoor, that could be outdoor, for all. Okay.
Okay, thank you.
Uh, who asked me the query? Santosh, you have raised the query.
Santosh, yes, yes.
Yeah, so this is common for the GIS as well. No need to record Assis on your behalf. I have doing the recording. I'm doing the recording. Okay, Assis. So you don't need to do. You will get the access. Okay, Assis. Yeah. So coming back to the to this IEEE. So whatever I'm going to discuss in the next 2 hours, each and every sentence I'm taking from this IEEE. This IEEE is a 200-page document, so you cannot read all 200 page. So I'll give you that which page is important, which formula is important, which clause is important. That straightforward you can study that, and in your free time you can study the remaining page, remaining formula. But what out of 200 page, what is that important? From that all we are covering here. Total out of 200 page here. So let us start with the basic concept. So first of all, before doing the calculation, we should know what would be the objective of the calculation. So the objective of any electrical installation, that could be any type of the earthing, electrical installation earthing, not only the substation. So and we, as we know, that objective of any earthing system is to provide a method, or we can say is to provide a path for dissipating electric current into the earth into the earth without going beyond any equipment or operating limits. This statement is important. Do not ignore this statement. Beyond any equipment or operating limits, we will discuss that what is the limits in the below slides, right? And to ensure that a person around grounded facilities is not exposed to danger of a life threatening electric shock, and to achieve the above both objective, we follow the below procedures. So what the procedure we are going to follow? First of all, we take that whatever our electrical installation, whatever we have the electrical installation, below the electrical installation we make one earthing grid. As you can see over here, that below this electrical installation we are making one earthing grid, earthing, sometimes we call this earthing mat, and from this earthing mat we are taking the riser, and that riser, this is called the riser, or rise. For taking this riser, again we take the earthing conductor, and with help of this earthing conductor riser we connect each equipment support structure with the common grounding grid. What I mean by that, you can, like, we can take this reference. So here we have one, like, electrical substation compound. So below this substation compound, below this compound we make one common grounding grid, grounding mat. If I'm telling the grid or mat, it means this kind of the grid or mat, this kind of the grid or mat. And from this mat we connect each equipment individually with help of the earthing riser conductors. So for the substation or switchyard earthing system, the common earthing grid is laid below the ground. And if I'm telling laid below the ground, so how much depth, what is the depth below ground? So IEEE telling that this depth could be in the range of 0.5 meter to 1 meter depth. And laid, and now the next question, who will lay, who will make this arrangement, the electrical or the civil? So that would be the responsibility of the civil contractor. Usually we take this work and we ask to do by the civil contractor, and laid by the civil contractors usually. So and here we can see the division of the responsibility between the electrical and the civil, that usually we follow during the substation construction, or when we are deciding the scope, then what the how we divide the responsibilities between the electrical and the civil. So the common statement that we follow: all earthing works associated with the earth mat within the substation compound shall be carried out by the civil contractor. All the earth mat. within the compound shall be carried out by the civil contractor. This shall also include providing branch connection which shall be extended and connected to each support structure. The below ground earthing mat shall be installed at a depth of 600 mm approximately. I will discuss about the 600 mm again once more. Below finished ground level, which we call as the FGL, the civil contractor will leave earthing tails, and that earthing tails that the civil contractor will leave, that would be approximately 1 meter long, near each foundation of the plant equipment, which shall be extended and connected to the support structure by the electrical BOP contractor. BOP, I mean to say balance of plant contractor, or the electrical contractor which is doing the work for the EPC or the electrical of the substation. So this statement you can see over here. Let me show you some side picture. Some side picture for this statement. As you can see over here, could you see this is the ground, and below ground, could you see here the earthing conductor rod? Could you see here?
Yes, sir.
I just take the some reference from the site. So I am telling that this electrical rod will be laid by the civil contractor, and he will leave the earthing is strip tail, and that would be approximately 1 meter. And when the electrical person will come, so he will extend that earthing tails, and that he will connect with the support structure of the equipment, that you can see over here. The same concept I explained with help of the drawing as well. You can see here we have the equipment. Here we have the earthing grid conductor that connect that in x and y direction, right? So this earthing rod by the civil, this earthing rod by the civil, and this tail is also by the civil. This earthing tail, or you can say riser, also by the civil, and he will leave the earthing tail near each equipment. And when the electrical work will start, so the electrical contractor will extend the tail and will connect to the support structure of the equipment, that you can see in this drawing as well. Could you see here? This is now the foundation of the equipment done, the grounding grid is done, and here you can see that near each equipment foundation the civil have like left here the earthing tail. Could you see here this one, this one? So when this on this foundation, when the equipment will be installed by the electrical contractor, and then this earthing strip will extended and connected to the equipment earthing structures. So I hope the division of responsibility is clear, that who will do the civil, that what would be the in the civil scope and what would be in the electrical scope regarding the, as I told, because we have to make the grid. So who will make the grid? The civil will make the grid, this kind of the grid, and he will leave the tail near each equipment foundation, and that tail he will leave near about 1 meter, near about 1 meter. But it is not that in 1 meter it would be 1 meter, it could not be enough in few cases. So in that case the additional conductor would be supplied by the electrical contractor. And few times we do the earthing of the bottom of equipment as well. Could you see here, like the bottom of the equipment or the top portion of the structure? So from here, from the top of the structure or bottom of the equipment, from here till here, this would be the responsibility of the electrical contractor. Yeah, am I clear with the with so far what I
Yes,
discussed?
sir, you are clear.
I discussed here the objective of the earthing, and to achieve this objective, what we do, we make a grid below ground. Depth of grid would be in this range, and this grid would be made by the civil contractor first of all, and civil contractor will provide the earthing till near each equipment foundation, which shall be extended and connected to each equipment support structure. and that connection done by the BOP electrical contractor. Okay, now so this is the system that we do, this is the arrangement that we do. Now let us come to the calculation and the drawing preparation. So to calculate that thing and to prepare the drawing, we follow the IEEE 80. And as I told that IEEE 80 have 200 pages, so which page and which formula is important. So in the IEEE 80, if you go to page number 92, figure number 33, so IEEE 80 page 92 figure 33 explain one design procedure block diagram which we have to follow. So we have to follow this block diagram completely one by one, blindly. Each what you written that we have to follow. Step 1, step 2, step 3, step 4. These all we have to follow. I'll show you this. I took this extract from the IEEE only. So which page I told? 92, right?
Yes, sir. Page number 92, figure 30.
Page 92, yeah. So IEEE 80, you come and you see page on the page 92 figure 33. So this figure we have to this we have to follow, and this block diagram is explained also. So for the explanation you can refer this one, 16.4 design procedure. So in the 16.4 design procedure, each step had been explained, like step 1 what we have to do, step 2 what we have to do, step 3. So each steps they have also explained here. So these steps 16.4 and plus this figure 33 we are going to follow for the entire calculations now. So I took this block and I took this design procedure block diagram and explain this procedure in a easy language so that it would be easy to adopt, right? So substation earthing calculations shall be performed based on the IEEE 80 standard page 92 figure 33, which explain the design procedure block diagram and well explained in clause 16.4 as well. So that would be reference of the calculations, the base of the calculations. So in this design procedure block diagram, if you see the step one they are telling we have to collect the field data. So they are telling A and to this extract could not be clear, so I can go directly here. Yeah. So step one they are telling field data, and for that they are writing here A and row. The A is indicating the area of the substation or switchyard. If I'm telling area, it means I'm telling about this length and this width, this A. So L into W, that would be A. And rho means the resistivity of native soil where we are making this construction. So that rho. But only two input would not be enough. We also required few other inputs. So that all I have mentioned here. Step 1, field data. Before starting the calculations, we must collect the field data, which includes the below data or below information. First, substation site area A. Area we need to calculate by the length and width for the earthing, because we don't have the area, we will get the length and width. So by multiply L into W, we can find out the area. Second, the soil resistivity rho. This we required as an input. Third data we required as an input is the fault or short circuit current and the duration of the fault or short circuit current for the earthing design. So current and their duration. Fourth input, what material we are going to select. The earthing strip metal, material type. Are we are taking the MS, GS, copper, what material we are taking. So that material selections usually we go as per the project technical specification, that what you are mentioned in the technical specification, because based on the material type the cost is linked. Copper have some different cost, aluminum have some different cost, so we have to follow that what is mentioned in the technical requirement of the project. For that we can refer some tender
Tender,
specifications.
sir, tender.
Right, so step one is this. Let us come one by one. Let us see all the four inputs in the detail. What mean by the A, row, and the fault current and the material type. So let us take the first input, the site area. So the site area L into W, it is too much clear, but I just explain or cover one more topic. It could not be possible that every time you will get the perfect perfect like a square or rectangle. You can get some different area also. So in that case, how you need to proceed, or how you could proceed for that, we need the substation area, site area, that can be calculated by as length multiplied by width. Lx indicating length into x direction, Ly indicating length into y direction, Lx and Ly. Whereas if the site is not a square or rectangle, then we can take the Lx as the max length of the conductor in the x direction. Like in this case, if you see, my site is not uh, ideal perpendicular rectangle. So in that case, what would be the Lx? So I will take the maximum length. So my maximum length in the x direction would be this b plus d. What I'm telling, that if you see, b is this portion, this much is b, and this much is the d. So b plus d is Lx. That would be Lx, and Ly would be the Ly would be the this much would be the Ly. So site is not a square or rectangle. In that, then we can take the Lx as the max length of the conductor in the x direction, and Ly as the max length of the conductor in the y direction. So that we have to take. I hope I'm clear with the site area.
Yes, sir.
So site area
Yes.
means so area. Now from where I will get the Lx and Ly, from where? So for that, you go and take your electrical installations. Means, let me take one reference project for the calculation as a reference. So I took here one project as an example. uh, one second. Kevin, please mute yourself. Background noise coming from you. Kevin, all of you, please mute. Right. Yeah. So here we have one reference project, which is 132 by 33 kV substation. And if you see over here, this is the plan layout. This is the plan layout, right? So plan layout. Here we have the transmission line, and a tower, dead end tower, taking the conductor entry into the substation. So this two is the line bay. This two is the line bay, and here we have the main bus over here, main bus, and here we have the transfer bus. The plan layout already we have discussed in the module number 7 in the layout module. So from there you can refer if anyone not getting the point, right? But for me, the important is the length and width of the site, length and width of the site. So this plan layout, length, length in x direction, and the width, length into y direction, that I need to follow. So what I do for that, I can go with the AutoCAD drawing of the this electrical installation, and uh, the parallelly one drawing would be prepared by the civil team, which is called as the foundation layout drawing. So I took the reference of the civil foundation layout drawing, which you can see over here. This is the similar kind of the electrical installation, as you can see. And let me open, I think I have their uh, electrical AutoCAD file as well. So here we have the control room building and here we have some water tank and firefighting pump house, DG set, road, and in this portion we are making the substation. So this length and this width. So this is the electrical layout, and for the grid, for the earthing, we are making one grid below the ground. So this grid we are indicating, or we will represent like this. Could you see here? I think this, you can see this is a kind of the grid or mat of the rod. grid or mat of the rod. I will discuss about the spacing.
Yes, sir.
This all things I will discuss later on. Just is this drawing appearing as the grid or mat or not?
Grid
That,
mat. Yes, sir. It is appearing as grid mat.
that we will make in the earthing layout. So don't worry about this. I am taking one already prepared layout as a reference. So
This is the Earth mat, na, sir? This is
yeah,
Earth mat.
yeah, earth mat layout. So I'm taking this uh, layout drawing as an reference only. Yeah. So what I need, Lx. So Lx, I will take the length into x direction. So how we can how yes, violet color. Yeah. So how we can say, we can ask our AutoCAD operator to measure the length in x direction, or you can also measure. So go to AutoCAD, go to the dimension, and then go click here the linear, select the point. So I took this the outer boundary, the first point, and then next point over here, and then I just measured about the length. So in the AutoCAD it is appearing, let me see how what length is coming, 126 meter. So I will take 126 meter length into x direction. Similarly, I will measure the length in the y direction here, and that length in x and y direction I will take as an Lx and Ly, and will multiply both, and then I will calculate the area A. The area A. A this area A is the multiplication of Lx into Ly. I'm parallelly coming to the calculation as well. So whatever the topic clear, I'm just putting in different color. So Lx 126 meter. I hope this 126 meter is clear. Lx is clear to all of you. Ly 75 meters, same, measure the length into y direction. What I'm doing, just to give you the one more uh, uh, view, what I'm doing, I'm measuring the distance from here till here. Could you see the this compound boundary? So
Yes, sir. Lx. Yes, sir.
from here to here I'm measuring the length through AutoCAD. After that whatever the compound we have for the substation, for that compound I'm measuring the length into y direction again. So from here this point, and from this point, this is the two in both end of the boundary wall fence. So just length. So this I'm putting over here 126 and 75 abbreviations. Let me go. And area, so area, what would be the area now? 126 multiplied by 75. Am I clear? J11 into J14, J11 this much, J14 this much, 126 into 75, it is coming
Yes.
9450, which is coming over here 9450.
One thing I want to ask is the bill of quantities will also be prepared for this.
Yeah, bill of quantity you have to calculate.
For earthing, yes.
Yeah. So you just measure the calculate this length all in x direction, all in y direction. Add both the length. That would be your length of the earthing rod. That we will do. That we will do. Okay. So coming back to the IEEE first of all. IEEE first of all. This A I took, my ultimate aim is to perform the calculation by following this uh, block diagram. So this block diagram I converted into this Excel. Like you can see, step 1 is step 2. So this step 1 step 2 is the same one, step 1 step 2, and in this Excel I'm putting the formulas. So Lx and Ly, this 2 is clear, A is clear. Abbreviations I'm putting, like what is the meaning of A. So this is the description of the A. Yeah. So I will explain the calculations. Parallelly, I will explain you the concept with help of this presentation. Now coming to the next input, which is the soil resistivity row. Soil resistivity row. So how the soil resistivity, or which value we will take. So usually for the soil resistivity value shall be performed by the Geoelectrical Investigation Agency. So by the geo-electrical investigation of the soil, the ERT we call as the earth resistivity test or the soil resistivity value is to be calculated by soil investigation contractor or soil investigation agency, and this calculation by that agency performed by the Venner's configurations, and the Venner's configuration is commonly used by the investigating contract agency. And in the winner configurations, what we do or what the agency that geoelectrical agency do. So in the winner configurations, all four electrodes are kept equidistance, and which is known as electrode separation along a straight line symmetrically over the measuring point, and soil resistivity is measured, and the average value of all soil resistivity data considered as an input for the earthing calculations. So I took here the reference of an ERT report. You can see the ERT from this ERT report here in the annexure one. This agency is putting their this soil ERT data. So you can see here serial number 1 to 10 and depth in meter. So 1 meter, 2 meter, 3 meter, like that depth they are taking, and then they are calculating the ERT for the 5 locations. So ERT1, ERT2, 3, 4 and 5, right? And in the ERT1, the location 1, maximum and the minimum, they are putting that what is the maximum resistivity, new resistivity coming, and then what is the average resistivity coming. So 36.419 plus 30.889, add both, divide by 2, it would be your average soil resistivity value, the average of the maximum and the minimum in the location 1.
So this is the standard method for the
Yeah,
this
yes,
soil
yes.
resistivity.
Correct, yeah.
So for each meter we have to take the soil samples, and then we will take the we will check the soil resistivity.
Yeah, soil resistivity. So
Okay.
and majorly we take the 4 or 5 locations we take, and majorly we take the important locations, like somewhere if we are putting the transformer, so that would be
Okay.
one kind of the major locations where we are putting the transformer, right?
Okay.
So we take the like the major locations, and for that resistivity we are the agency. This is done by separate agency, not by electrical engineers, but just to get you a feeling of that. Due to that, I take the extract of the one ERT report.
And this is same for also GIS also.
Yeah, yeah, yes.
Okay. Okay.
Yeah, yeah.
Sorry, depth. Hello.
Yes.
Avinash here. Actually, this is, if I'm not wrong, this is not, it's the distance between the four electrodes. P1, P1, P2, C1, C2. The depth. I think by
No,
mistake
no,
the
no,
typo
no.
error is there. The
Not that,
distance between.
not the four electrode distance. This is the depth in meter.
So up to the 10-meter depth we have to go and measure.
Yeah, for each for 4 or 5 locations.
So this excavation we have to do on the substation, 10-meter up to 10-meter depth.
Bore.
This not you. The soil investigation agency will do, and they will do the boring there for that.
Actually,
Because presently we also doing the soil resistivity. Okay, might be some factors are there.
Maybe. What I do, I'll share you one complete ERT report that you can go through, Avinash.
sir.
Okay.
Okay, Rahul.
That you can take as a reference.
Sir,
Yeah.
I have a report of soil resistivity. They have given only 1 points. They have done a soil resistivity at a place. There are only 1 points they have considered for this.
So
For the test
you
of
do
resistivity.
assessment at which point they have considered the maybe area of the installation would be lower. In that case, they I think they have done. But take that which point they have considered. If the one point should take that point near to the transformer area installation point, but one
Okay,
point I don't think
and
that
depth
one
is
is.
also, sir, because they have done only the spikes. They use the spikes for the finding the resistance of the soil. They have given only this. This is a soil investigation report. They said that this is a soil investigation report. and only this
Okay,
is
I will use
valid.
here. I will check. I will use here. I
They
will.
doesn't adopt this method for the
Yeah, use here.
finding the.
Yeah, but one place would not be enough, Vina. So you share the report. I will go and go through.
Okay, sir.
Okay, and I will share one report to you as well. That also you can study.
Okay, sir.
Okay, coming back. So we have the ERT1, ERT2, 3, 4, and 5 all. So and in the 10 depth we are taking. So all the 10 depth again we are calculating here the average of the all 10 depth. So ERT1 average adding all divide by 10. So 41.563 for the ERT1. Similarly for the ERT2 average, ERT3 average, and ERT4 average, and ERT5 average. So putting all the ERT1 to 5 average over here again. So serial number 1 to 5, location ERT1 to 5, and then average resistivity of all the locations. So 41.56, 37.27, putting all the 5 values, and then again adding all these 5 values and divide by the 5. It will give us the average soil resistivity value in ohm meter that we can consider for as an input in this calculations. In this calculation, rho means this rho, right? So I hope that this a and rho, this two input is clear. Now coming to the third input which would be required, it is not mentioned here, but that would be required further in the calculations when we will calculate about the conductor size, the fault or short circuit current. So that also we should know. So the fault or short circuit current and the duration of the fault current for the earthing design. So in the last Sunday class we have discussed about the short circuit current. We have calculated with help of the ETAP, right, for the industrial electrical
Yes,
installation.
sir.
Okay, now when the case of the switchyard will come, when the case of any electrical substation will come, in that case whatever we have discussed in the last Sunday class, that would not be applicable accurately or totally. We have to we have to follow a different approach for the short circuit or fault current. So that what could be the approach, and if you remember in the starting of the training session we have discussed the short circuit current for any solar power plant substation. We have discussed.
Yes, sir. You discussed about short circuit force calculation, and second method you also talked about taking from the tender
Yeah.
31.5 and 40 kilo ampere 50 kilo.
Yeah, so now just recalling those point again for the with respect to the earthing. So which fault current we should take for the short earthing calculations? There are too many type of the fault current. Like as we know that fault current could be divided into two part, symmetrical and the unsymmetrical. And the symmetrical fault current again could be the triple L type fault, triple L2G fault, and the unsymmetrical could be L2G, double L2G, this kind of the fault, right? So which kind of the fault current we take for the earthing calculations? Ideally telling, in the ideal situations, because earthing we are making that if any fault current, earthing we are making that if any line broken, if any line conductor broken, and that coming down on the ground, so what current will flow in the earthing system, are and based on that we need to design the earthing conductors, right? If suppose this earthing, the earthing conductor broken and coming in contact with, if in case it this conductor will broke, so what will happen, this conductor will come in the contact with the equipment outer enclosure as well, right?
Yes, sir.
So and here we have done the earthing, so in that case ideally we should consider if any line to ground fault happening, so what would be the line to ground fault current or short circuit current, and based on that the earthing conductor should be designed. This should be the ideal case. But what happens? Coming for the short circuit current, ideally the line to ground fault, also called as 3I0 or zero sequence current. During the ETAP, we will discuss about the sequence, positive sequence, negative sequence, the zero sequence. And the zero sequence we also called as the 3I0. So ideally we should take the 3I0 or the zero sequence current needs to be considered, and if in case 3I0 or zero sequence current value is not available or not present, so in the absence of zero sequence current or in the absence of line to ground fault current, we can take three phase fault current as well. But that is not, if in case we have line to ground, so no need to go with the three phase fault current, go with the line to ground fault current. And this I naught value, this line to ground fault current value, this needs to be decided by a system study of the complete connecting network. For example, the interconnecting line root length, cross. One more important topic, concept, please keep in the mind that suppose here we have the electrical installations. Let me go here. So for the electrical installations, if any fault is happening, so there would be two sources of the fault current, like what I can say, uh, are two paths for the fault current. So if any line to ground fault occurred here, so in that case, who will be the source of fault current? The source of fault current. What would be the source? Obviously, this transmission line conductors, and
Yes, sir.
which is connecting somewhere into the somewhere back to the
Transformers.
back to the source. So that source would be the, so from that source have some impedance, source have some voltage, source have some current. So through that the current will feed it through this transmission line conductors, and that would impact that what would be the current will flow locally in the grid. So always consider external source, do not consider the internal source. If in case internal source is internal fault current happening, so in that case the equipotential case will develop. So in the case of equipotential, the touch or step voltage will not develop. So for the any kind of earthing calculations, we take that what would be the source fault current, external fault current coming from the source, our source fault current we take in that case. So
About these internal and external
I will come, Jignesh, in the ETAP module we have for that, and in that case we will discuss about the short circuit current in the detail. Okay, I'm just giving you one approach, one mindset. Coming back to the fault current or short circuit current, so directly stating here. So ideally we should take line to ground fault current. Point number one. Point number two, this need to be decided by system study of the complete connecting network. For example, interconnecting line root length, cross section area of the interconnecting line, number of connecting terminal lines, phase to earth fault level, data value with one bus away in the system. So by taking all this value, we decide that could be the line to ground fault current, and ideally that all above data and the line to ground fault current value is the responsibility of the grid operating company to provide to the EPC company or to the design consulting firm, and considering these input, the EPC company or the design consulting firm will perform the calculations. This is the approach one. Second approach, in developed country, it's these are system study data in the developed country, like if we go to the European country, so in that country it is easily available. But in the case of developing country like India, developing countries not fully developed, so that are easily not available. In that case, to design the earthing system, but we have to do the earthing, and for that we have to do the earthing system design. In that case, the grid three phase fault value could be considered as the fault current or short circuit current. Or the another approach or alternative option, if in case I'm taking the three phase fault current value, and that value, because this is three phase fault value, so that value would be higher than the single line to ground fault current value most most of the time, right? Am I making the sense? Am I making the sense? I'm just trying to develop to create one concept about the fault current or short circuit current.
Yes, sir.
So the case one, this is the ideal case. Case two, let me take the snapshot. Let me take the snapshot. Please connect with me, because this could be one important consideration. So the point one, so this short circuit current, again I'm going to divide into the too many approach. First approach, take the 3 I naught current. This is the approach here. I request all of you, please connect over here. I have a lot of things to discuss, and again, time is shortage. So, if you consult, I can speed up my discussion. 3 I naught. This is the first
Yes, sir.
Okay,
approach.
sir.
Yes, sir.
Second approach. But if in case I don't have 3 I naught, what I will do? Because most of the EPC companies and consulting firm in the developing country, they didn't get this value. So what they will do are, in suppose you are the design engineer in that company, so what you will do? Don't stop the calculations. Go and select the three phase fault current value, grid three phase fault current value, and this grid three phase fault current value you will get in the electricity authority, CEA, right? Central Electricity Authority. I think these all things already we have discussed,
Yes, yes,
already
sir.
covered. But again, I'm discussing because few is the new enrollment, few is the new student joining
Yes, sir.
today. So only for those who are joining first time today, I'm covering this again. So these three phase fault current value, you will get this in the grid regulations, and in India we follow Central Electricity Authority this grid regulations. So go into Central Electricity Authority, and I took the snapshot from the Central Electricity Authority, and here for each voltage level the three phase fault current value is mentioned. So select the value. If you are working for 66 kV, select 31.5 km for 1 second. 132 kV, select 31.5 or 40 km for 1 second, your fault current and the duration. For 220 kV, go with the 40 or 50 kilo ampere. For 400 kV, go for the 50 or 63 kilo ampere. For 765, go with the 40 or 50 kilo ampere per 1 second. And if I check in this calculation, if I check in this calculations, I can tell you the fault current is 31.5 is considered here, because as I told that this is 132 by 33 kV, and as per the grid regulations the fault current is for 132 kV 31.5 kilo ampere. Due to that reason, in this calculation it has been considered, and this calculation which I am telling you, this is the approved calculation by the power grid. Few places we have done the revision based on the revised incorporating the PGCL comment, right? So on that places it is put R1, this R1 some where we have revised after the power grid comment. Anyway, so if you see in this calculation 31.5 kiloampere is considered, which I'm telling you the second approach, second approach, you go with this 31.5 kiloampere, right, for 132. Similarly for each voltage you can select third approach. But what will happen when you are doing the calculations, you are taking three phase fault current value which would be higher than the line to ground fault current value most of the time. It may be case that your earthing is not safe. Earthing is not safe. What I mean by that, I will cover this point. The safe of earthing system means the ground potential rise, the touch voltage, stub voltage is not coming below the acceptable limit. So in that case, we say that earthing is not safe. In that case, or if in case your soil resistivity is too much high, like 400 native soil resistivity coming 500 ohm meter, and if you are taking such a high grid fault current, you are taking the entire grid fault current, it could be case that you could not achieve the safe earthing. In that case, what could be the approach third method? You can calculate, if the safe design is not possible to achieve, in that case the fault current contributed by the source network, which I just explained. The fault current contributed by the source network, this one. If I Source network can be calculated and that value can be considered as an input. So third approach, and in the third approach, you calculate the fault contributed by the source network and that you take. So what I'm doing in that, I'm taking 31.5 kiloampere is my grid fault level, and I'm connecting this substation. I'm connecting this substation from the grid somewhere. So this conductor have some resistance and the reactance. So this conductor will have some impedance. So due to the impedance of the conductors, the fault current which is reaching at this substation level, that would be lower than the entire grid fault current level. Is it making sense? So why lower? Why
Current will be lower due to the impedance.
Impedance of the transmission lines, conductors, right?
Yes, sir.
If in case it is 20, 50, 60 kilometer length, so the 60 kilometer length will have some impedance, so that they are going to reduce the current at this substation level. This point we have discussed in the initial days, yeah, when we started about the
Yes, sir.
short
You
circuit.
discussed it about the short circuit force
And we have done the calculation as well.
Yes, sir.
The
Thevenin impedance. Yes, sir.
Yes, with the impedance method, we have done the calculation for the solar substation. We consider the solar substation, and for that we have done this calculation. Am I clear with this three approach about the short circuit current? Short circuit current approach one, ideal 3 in I naught, backup 31.5. If with the help of the backup could not achieve the safe, so go with the uh, fault current contribution by the source, and that fault current value you can take. Yeah, Ghosh, you have the access of the previous recording, so please once go through. I have discussed this point in the detail. And if you couldn't understand, message me. I will discuss one to one with you. Okay, Ghosh, is that clear with you? Actually, what happened if I go to the this source network current calculations? So my earthing topic will left. So I don't want to miss the earthing agenda today. Okay, so uh, that's the reason you go through, and if not, yeah, yes, you look there, and then if not, you let me know. We can discuss after the class. Anyway, so so to achieve this value, so for today calculations, I'm going with the grid fault table, which is 31.5 kilometer as an input. So I'm going to put this one as yellow. I hope you all agree with this. Okay, now coming to the fourth, yeah, coming to the, so I think we have covered all the A and row. So A is covered, this A is covered, row is covered, fault current is also important, and the material, and the about the material. So the about the material type, we will go and do the selection as per the project technical specifications, and based on that we will select. Let me open one tender. for the power grid as well, and let us see what they specify in their tender technical specifications for the material. Just give me 1 second. Tenders, yeah, tender document for the power grid, suction switchyard erection, division 9. Technical specification for the switchyard erection, yeah, substation erection. And in this erection, because earthing is part of the erection of the substation, and earthing is the first like activity that we perform at the site. So earthing and foundation both is the activity that done at the site initially. Okay, so let us see the earthing. So here, if I see, as I told here, that earthing material type as per the project technical specification. So I open here one power grid technical specification, and in this specification, earthing conductor specification, all conductor buried in earth and shall be made mild steel. So we have to take, if I am doing this project, power grid project, so I have to take MS. Buried in earth, buried below depth, below ground. All conductors above ground level and earthing leads shall be galvanized steel except for the cable trench earthing. The minimum size of the conductor to be used as indicated in clause 9.4 of this section. So here they are telling us the MS. So 9 come to the 9.4, and here we can see the detail about the earthing. Yeah, earthing here. So here they have given the detail in the earthing material and the size as well. So size we will calculate. And if I'm doing this project, in this project, no need to do the calculation directly. You can go and select 75 by 12 mm GS flat for the leads and 40 mm die for the earthing rod. For this project, calculation would not be required because it is already given. But for any solar project where we don't have any value, so we have to perform the calculation. So we will perform the calculation as well. Yeah, bare as well. Yes, copper can. So as I told, go as per the project requirement. Okay, so copper is also considered. Like in India, we generally not consider. But if I go out of India, like in Middle East, in European and in the UK, they go with the copper conductors. Usually 40 by 5 copper conductors they considered. And please put your name. I won't put your original name.
Yeah,
Yeah,
Mr. Raghav, this is Avinash. Sorry for
Avinash, put your name. Yeah, okay, coming back. So I hope this fourth is earthing strip metal material type is clear. What would be the approach for you? Go take see in your technical requirement, technical specification requirement. So step one is clear. Step one is the clear. Now coming to the step number two, conductor size. So let us do the conductor sizing, right? What I mean by the conductor size, which conductor size I am telling, which conductor size I am telling. I think I have one reference video. Let me tell you, show you the video as well. Just 1 second. Thickness. Let me start from again. Thickness. 75 mm, right? Okay, thickness. 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 Thickness कितना? 10 mm. Yeah. So this is one example of the earthing strip that we are using. So we will calculate this earthing strip like length and the thickness are that I'm telling is the size. So I will calculate the size. Thereafter, this length and thickness we can recalculate. We can calculate again. So coming to the earthing conductor size, how we can calculate the conductor size? For that again, go to the IEEE 80, go to the formula number 37, clause number 13, 11.13, conductor sizing factors. Take this formula. So the earthing conductor could be calculated by help of this formula. Area. So now this I is equals to A mm square. A is the area. A is the conductor cross section area in millimeter square. So A would be I divided by all this much. Under root T cap 10 to the power minus 4 divided by Tc alpha R rho R ln k0 plus Tm divided by k0 plus Ta. Right? That would be the A. A would be I divided by this much. Earthing conductor size shall be calculated as per class 11.3.1 formula 37, and the constant value, because here if you see T cap is the constant, alpha R rho R is the constant, K naught and Tm is again the constant, T is the ambient temperature, so that would be your site temperature, not the constant. Tm would be the constant based on temperature based on the material type. So all these constant value we can select from the table 1 of the IEEE 80, right? So again go to the IEEE 80 here, go to the table 1, go to the table 1, and in the table 1 all the material constant is given, then select. Yeah, here we have the table 1 material constant. So here the formula that we are taking, this formula, or you can rewrite this formula like this: equation 40, it would be I divided by T cap 10 to the power something. So this formula we have mentioned over here. If you see this formula, in this particular case I have considered soil resistivity as the 100 ohm meter. In my presentation I took the reference from another ERT report. It is coming 37.42, right? But for this project, 100 ohm meter was the soil resistivity, so that I am putting over here. So soil resistivity. Coming to the conductor size, so area, this conductor area would be I divide, area would be I, and this all coming in the division. T cap this value. So this value I am taking from this reference, this one, this reference. Okay, and putting the values now, and the values we can see in the table 1. If in case I'm taking the ms, which is means steel I'm taking, so for the steel I can go and select the values here. So go to the steel and select the values over here. Steel and 605 would be my K naught, alpha R would be 00160, K naught this much, Tm is like 1510, alpha R1 15.90, T cap is 3.28. So putting all the values here again, coming to the abbreviation I'm putting here again. So fault current is clear, fault distance is 1 second. So this is also clear, right? Alpha R I'm putting 0.016. So where this value is coming? 0.016. Could you see over here the alpha R? 0.016. Actually I'm putting all the values in the Excel, then it
Yes.
will calculate through the Excel. So 00160, right? And then after that row resistivity of ground grid conductor 15.9. So where is the 15.9? Yeah, row here 15.9, right? 15.9. Generally you we take the steel 1020, yeah, Nimesh. And then T cap 3.28 over here, 3.28 over here, 15 1510, where is 1510 over here? So I am taking this value and putting over here. So this all is clear, and now we have the I, which is 31.5 kiloampere. So putting all the values in this in the formula, in this formula. So A would be I, which would be 31.5 kiloampere or 31,500 ampere, divided by T cap. Put the value of T cap. What is the value of T cap? Which is 3.28. 3.28 into 10 to the power minus 4. TC is the fault duration, which we will take as the 1 second. Right?
1 second.
Alpha R, rho R. Alpha R, rho R is already given over here.
0.0016 alpha.
Log ln K naught plus Tm. K naught, here we have the K naught value. K naught again take from that table. K naught from that table only. Tm is the maximum fusing temperature, so that would be 1510. divided by TA would be your ambient temperature. So ambient temperature, take your site temperature, and that generally we take as the 150 degrees Celsius. So TA would be 50 degrees Celsius, right? So putting all the values, we can decide the earthing conductor size, which is coming over 256.23 square mm. That would be the size. And if I know the area, so I can calculate the diameter, and I can calculate the uh, I can convert the area into the rectangular form as well. So how we can calculate? Coming to the earthing strip that we use. So if you see earthing strip we use in this shape. So now we have the area. This area is coming to 56.23. So how we can calculate? So we know the area. Or let me take a snapshot from there. Just that would be clear. This is a side photo of the earthing strip. Yeah, so we have calculated the area, right? Area is we can write area as the pi r square if I'm taking the shape of the earthing conductor into the circular shape. In that case, if I'm taking the earthing is conductor in the rectangle shape, in this shape, so this area, like I'm taking this shape, right? So this area could be length in. So which length? Do not take this much total length. Due to that purpose, I took
25.
I
Cross section.
yeah
Thickness of the
yeah. Due to that purpose, I took the snapshot from the side. So this L I'm telling means this L, right?
25 mm.
This L, and W which I'm telling this W,
10
this
mm.
this W, right? So we know the area. In my case, the area is coming to 56.23 something, 256.23 something, right? So 256.23 something, this area is coming. So this we can convert in the equivalent L into W. But before converting the equivalent L into W, we have to consider the few margin as well. So what would be the margin? And by this margin we need to consider, before converting, let me cover one more important topic, which is the margin. So when I'm putting the earthing conductor below the ground, so the ground have the moisture, and that water content in the moisture formation will do the corrosion on the earthing conductor. So due to that purpose, we have to consider the additional earth, corrosion allowance, right? The possible exposure to a corrosive environment should be carefully examined. It may be preferred to choose a larger conductor size to compensate for some gradual reduction in the conductor cross section during the design life of the substation, where the soil environment tends to promote corrosion. So see, so for that purpose, we can take the reference. So I took here one extract from the CBIP manual, and if you don't want to go with the CBIP, in that case, you can go with the IEEE 112 as well. IEEE reference, IEEE transaction of power apparatus and system, and this IEEE is also telling about the corrosions. So this is the one method if you don't want to go with the CBIP, which is Indian standard. So go with IEEE, and in when it comes to India, so we go with the CBIP manuals. So as per the CBIP manual, usually we go with the CBIP manual. So as per the CBIP manual, they are telling that if I am putting the conductor, in the case of conductor to be laid in soil having resistivity, which resistivity I am talking about? So this ERT, this resistivity. If the resistivity is soil have resistivity greater than 100 ohm meter, or 100 ohm meter, in that case, no allowance we have to consider. If in case the soil having resistivity in 25 to 100 ohm meter, then 15 percentage allowance means multiplied by 1.5. Greater than 100 ohm meter, so no allowance. 25 to 100 means in the case of 100 you have to consider 50% allowance. At 100, 15% allowance we have to consider. So multiplied by 1.15, whatever the size you have calculated. In case of if the soil having resistivity in the range of 25 less than lower than 25 ohm meter, in that case the allowance would be 30%, means we have to multiply it by 1.3. Coming back to the calculations here, if you see 18.06, in this 18.06 we have done multiplications because in this case the soil resistivity is 100 ohm, so 15% we have to take. So take this value 18.06 and in this value multiplied by 15%, so 21 mm it is coming, 21 mm, right? Or we can take this value 256.23 as well. So take 256.23 into 1.15. 18 mm we have calculated for the rod diameter, but before that we can multiply in this also. So 294 point something, or we can see it would be round figure 300 mm square, right? 300 mm. So I can take this 300 square mm here as well. Am I clear that with this 300 square mm? 300 square mm equivalent LNTV we can select. So we know that what the size comes in the market for the earthing strip. It comes in the range of 25 into 3, 25 this 3 this, it comes 50 into 6, it comes 75 into 8, okay, and 75 into 10, 75,
50 into 10.
yeah, 10,
50 into 10.
yeah, 15,
50 into 10.
yeah, okay, 15 into 10, that I have not seen. Anyway, 75 into 10 as well. So these are some standard earthing strips available in the market. So out of the market availability we have to select. So here 300 coming, ideally we can go with the 50 into 6, 50 into 6 because it is matching with the 300. So 50 I can take over here, 6 I can take over here, right? In my case, and okay, and
So this is the size of risers, no?
yeah, no, the size of the riser, uh, and if you are putting the grid as the strip, then this could be
Okay,
the
okay, okay.
size of your earthing grid as well. Now,
Okay.
as I told that in case of the making the grid, we take usually the rod conductors. Rod will come in the circular form, so we can convert the area into the we can calculate the diameter of this rod. So for that, a would be pi r square, so A would be pi and r radius, that could be half of the diameter, so r A could be d by 2 and then square of this, so that could be A is equals to pi and then d square by 4, and then d would be 4 into A divided by pi square root. So d would be under root 4 into A, what we have calculated. You can take to 56.23 and then in the last we will multiply it by 1.5, 256.23 divided by pi value 3.14. Calculate this value and I think this value is coming near about 18.06 millimeter, right? And in 18.06 multiplied by 1.15 for the corrosion allowance, it is coming 21.56 or 21 mm, right? But I am not doing 21 mm. If I am making the solar power plant, I will go 21 mm or 30, 25 mm. But in this particular case, because this is a power grid project, so the power grid is telling in their technical specification that earthing conductor rod diameter size would be 40 millimeter dia. Main earthing conductor to be buried in ground, 40 mm dia. So what I did here, that I calculated that whether 40 mm dia is enough, is safe or not safe. So as per the calculation, 21 mm is coming. So 40 mm is I am going. So the 40 mm would be, obviously it is double of the requirement, so that would be more safer, right? But if in case you don't have the 40 mm, you go with the 25.6, right? I will, this is the, this 21 mm is your minimum requirement that I can say here, right? Am I Correct. I can say minimum requirement 21 mm, right? I don't think
Yes.
I have any concern with this. 21, you can't go below 21.
Yes.
Above any size you can go. Above size you can go, or you can select the technical requirement of the project. I will here there would be one uh, case study as well. So that case study I will discuss later on. The case study would be kind of the solar substation. In that case, we do some modification. So that I will cover later on after completing the entire calculation, because that case study is only for the solar power plant, and we do some addition in the conductor size because the area is less due to that reason of the solar switching substations. Okay, so step 1 and step 2 is clear. Step 1, step 1 and step 2 is clear. Am I clear with this step 1 and step 2?
Yes, sir.
Yes. Yes.
Okay, and additional is also clear. Now coming to the third step, which is the step 3, touch and step criteria. But before coming to the criteria, let us understand what mean by the touch and step voltage. After that, we will come on the criteria. So what I mean with the touch and step voltage, as I told you that the objective of the earthing is the ins- and to ensure that a person around the grounded facilities is not exposed to a danger of a life-threatening electrical shock. So keep this line in the mind, and after that I will come on the touch and step criteria. And one more important point, keep in the mind that in the beginning we have discussed something about that how much current a person could withstand or could carry without any dangerous situation. So this IEEE is telling that 116 milliampere or 156 milliampere person, 50 kg person and 70 kg person can carry. Similarly, we when the fault is happening, we can calculate that, or forget about the fault. Let us go with the ideal. Similarly, we can calculate that how much voltage a person could withstand, right? Same as you have seen the how much current a person could withstand.
Yes.
Same as the same concept. So before going to this touch and step criteria, I'm telling you that the basic concept that how much the voltage. After that, I will come on the touch and step voltage. So let us see. Let us see. The step 3 would be the touch and step criteria. Before that, let us see what is meant by touch and step voltage. Touch and step voltage, and then I will come on the calculation. So what I mean by the touch and step voltage. So these are the some shock situations, basic shock situations. This is I took this extract from the IEEE only. Go to the figure 1 of IEEE. You can get this kind of the. This could be the shock situations. Means in any substation. This here you can see this is the like fence, and here we have some metallic structure, and then here you can see that here we have the transformer, and then it is, and this is the case of the GIS. So duct is going inside the GIS building, right? So where what could be the situation of the shock? So the two situation is coming most of the time, because this situation would be very less metal to metal touch voltage, because we are putting a distance between two metal. So that situation would be less, right? What could be the case? This could be the case the person is walking in the substation and their foot is separated, and the ideal separation distance we take 1 meter, and then if any line to ground fault happening, the fault current is flowing through the soil resistivity. Soil do not have the uniform equal identical resistivity. So each soil have different each soil layer will have different resistivity. So due to that, at each point, at each piece of distance there would be different voltage, because the fault happening soil have resistivity. So I into soil resistivity, that could be the voltage that may generate at the event of the fault. And when this two feet separated, so there could be case that both foot is on the different uh, soil potential, are right. And due to that difference of the potential, there could be case that the current can flow through the person. If you see here, this is the graph indicated, like graph indicated. So means this is a like a graph of the how much, like if you see here, surface potential profile of the like soil. So the foot could be under two different profile. So there would be difference of the potential. Due to that difference, the current will flow. So this could be one shock situation for the person. Second situation, that if person is just touching the hand to any faulty equipment. Third position, that person is not touching, only they are completely in touch with the faulty equipment or the equipment where the fault has happened. So IEEE is like explaining different shock situations, and based on the shock situation, they calculate the voltage for each shock situation. So the one voltage that they calculate, that if the person is walking and their two leg is separated by 1 meter, so what could be the voltage between both the leg or both the step, and that voltage they are referring as the step voltage. Second case, if the person is touching, so in that case, equipment may have the different potential. The person may have on the different potential. So due to that difference of the potential, again the current may flow, and again the shock may come. The electrical shock may come to this person. So this situations, the IEEE telling us the touch voltage situations. So touch voltage means when the person is touching to any grounded metallic object. So between the grounded metallic object and the person touching, so what the voltage develop, this voltage they are telling as the touch voltage. Third case,
Uh,
if the person is completely in touch with the faulty equipment or equipment, in that case, in that case uh, the this in this case, what the voltage generated, so IEEE it is telling this voltage would called as the mesh voltage. Mesh voltage is also called as the maximum touch voltage, right? So these are the cases. So the touch voltage, I'm before coming to the criteria, I'm telling you the sense are what the meaning of the touch and mesh voltage are, the touch and step voltage. So the first I'm taking as the touch voltage. So touch voltage would be two kind. One is the touch voltage, one is the mesh voltage. Touch voltage is just person is touching the equipment, and then what voltage generated, that would be touch voltage. The potential difference between a grounded metallic structure and a point on the earth surface separated by a distance equal to the normal maximum horizontal reach of a person, and that take as 1 meter, right? So this, in this situation, what the voltage generated, that referring as the touch voltage. Mesh voltage, the maximum the touch voltage value is called as the mesh voltage. Similarly, when the person is walking, and here we can see one graph of the electrical potential. This is calculated with help of the CDEGS. So if you see here, when the fault is happening, so each piece of the land have different voltage profile. So if you see that on the corner we have 8942.79 voltage generated on this rod. Because why this voltage, high voltage coming there, because we have not used the earthing rod, right? And when we are coming towards the uh, equipment, where equipment installation and where we have made the earthing rod in this area, the touch voltage is 1518.18. This not the touch voltage, the uh, developed voltage. It is coming 1.18 voltage, and when I'm going up away from the grounding grid area, in that case the ground potential profile is increasing, that you can see here, like 2341 this color, and then 3166 this green color, and similarly it is increasing, right? The step voltage, the potential difference between
Yes, sir.
points on the earth's surface separated by a distance of the approximate 1 meter is called the step voltage. So this is the touch and step voltage definitions. This is shock situations cases that we can see over here as well. The shock situation place that I think through the SCDGS is obtained. So this is the kind of the electrical installation again. So here we can see touch voltage, step voltage, touch voltage, touch voltage, step voltage, and reach touch voltage. Reach touch voltage. Usually we take the touch and step voltage and the maximum touch voltage. These cases. So these are the soft situations cases. So and now as I told, as we have discussed that a 50 kg person can withstand 115 milliampere or 116 milliampere current, or a 70 kg person can withstand 156 milliampere current per duration of 1 second. And if the duration is reduced 0.5 second, then the same person 50 and 70 kg person could carry this much current, right? And this current we are calculating with help of this formulas, and here we have the table for the different shock situations. Second, the current withstand capacity of 50 kg 70 kg person. Similarly, we can find out how much voltage if 50 kg or 70 kg person withstand or tolerate with help of the IEEE, and that would be the standard voltage irrespective of fault. Current depends only on the shock duration and the resistivity of the soil and the resistivity of the surface. And these voltage are the two types: tolerable or acceptable touch voltage, and that we have discussed here, the tolerable acceptable touch voltage. So touch voltage is clear. Touch voltage, this word is clear. What I mean by the tolerable or acceptable means how much voltage a person could tolerate without serious injury. Am I clear with the
Yes, sir.
tolerable touch voltage? And the tolerable step voltage or acceptable step voltage means how much voltage a person could withstand, could tolerate without serious injury, irrespective of the fault current, just with uh, taking the weight of the person and the resistivity of the soil where they are standing. So this could be calculated with help of this formula. This could be calculated with help of this formula. uh, Step and touch voltage criteria. I again take the reference from IEEE clause 8.3 step and touch voltage criteria. So now coming on the complete word criteria, what I mean by the criteria. So before coming on the criteria, let us see how to calculate the value. The safety of a person depends on preventing the critical amount of shock energy from being absorbed before the fault is clear and the system de-energized. The maximum driving voltage of any accidental circuit should not exceed. Please concentrate on this statement. Maximum driving voltage of any accidental circuit should not exceed the limit defined as follows. So here this formula defining the limit of the tolerable or acceptable touch and step voltage, and when the fault happening, so whatever the voltage developing, those voltage should not exceed these limit values. So for a body weight of 50 kg, the E step would be the 1000 plus 6 into Cs into rho s 0.116 divided by under root of Ts. Remember, this is your current, right? 116 milliampere is current. Your current right now.
Yes, yes.
116. Let me correct.
Yes, sir.
116
Yes, sir.
current. So I'm dividing the voltage. So I'm dividing the current with help in the factors. This factor is what? 6 CS into rho s into under root TS. TS is your shock duration, right? 6 into CS. CS is, we can calculate CS value with help of this formula. CS is equals to 1 minus 0.009, 1 minus rho divided by rho s. Rho is native soil resistivity. Rho s is your surface resistivity, and we know that on the native soil we put a layer of the rock, right?
Yes.
Stone spreading we do. So the rho s would be the resistivity of the stone that we are spreading, and the spread depth we take in the range of 50 mm to 150 mm. So this rho s would be your stone resistivity, and which is called as the surface layer resistivity. So 1 minus rho is, yeah, gravel resistivity. So 1 minus, yeah, graveling resistivity. So rho is soil ground resistivity. So 1 minus rho divided by rho is divided by 2 HS. HS is your depth of the gravel plus 0.09. Putting the value, we can calculate the CS. Put the value of CS into this and we can find out the step voltage. Similarly, we can find out the touch voltage. So E touch, by mistake in the IEEE it is written as E step, but it would not be step, it would be touch. This is a printing mistake in the IEEE. The touch voltage, so E touch 50, 1000 plus 1.5 CS into this 0.16 into TS. Again calculate the touch and step voltage from this value. So I am putting this value in the Excel formula and calculating the values here. So CS 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 0.0091 minus rho divided by rho is. So let me come on the row. Let me show you the now soil resistivity 100 ohm meter. It is very much clear. Ambient temperature 50 degrees Celsius. It is clear. Now rho S. So if I consider the rho, just let me go here and let me see that what the resistivity of gravel we take. So if you see over here, the resistivity of the stone for spreading over the ground shall be considered as 3000 ohm meter under wet conditions. So usually the gravel stone resistivity is considered as 3000 ohm meter. This is also mentioned in this technical requirement as well. So this we take, so rho s would be my 3000 ohm meter. So I am putting surface resistivity as 3000 ohm meter, and if you wanted to take the reference from the IEEE, so you can go table number 7 of IEEE 82000, and in that table also you can see. So go, let us see the table number 7, table 9. So table number 7 will give you the range of the soil resistivity. Table number 7, typical surface material resistivity. So here, description of the surface material, resistivity of sample ohm meter, dry and wet. So crusher non-granite with fines. If I take this, in that case, this would be the resistivity. This resistivity value, granite we have to take. You take is reverse, right? So crusher round, vast granite size unknown, and vast limestone. In case of the substance, we take this kind of the surface material for making the gravel. Size is not 100% none, and vast limestone. This material, and in the case of the wet, the resistivity we take in the range of 2000 to 3000 ohm meter, but we go with the higher resistivity. So if the resistivity of the surface will be higher, in that case the probability of current coming return over the surface would be lower, right? Because, and if I take the high resistivity, in that case your contact resistance would be higher. So we'll generally go with the uh, like highest value. So 3000 ohm meter we considered here. So putting the value of 3000 ohm meter over here, now we can solve the CS. And let us the CS, what mean by the CS. Again we can see CS, the formula we have seen for the CS, but let us see the CS again with help of the rho s. So here it is the formula CS, and CS is what? CS is what? Let us see the CS is what? Just typical shock situation, so that we have seen. Just 1 second. Yeah, so CS is derived here. Effect of a thin layer of surface material. It is the effect of a thin layer of surface material, and that we are putting the layer of the gravel, and that thickness we take in the range of 0.08 to 0.15 meter, right, or 3 to 6 inch, and in the simple language we take 50 into 150 millimeter. In this range thickness we take uh, for the gravel spreading in the substation. So they are telling that if the underlying soil has a lower resistivity than surface material, will only some grid current will go upward into the thin layer of surface material, and the surface voltage will be very nearly the same as that without the surface material. So you can go through and this and study this theoretical statement over here. I'm coming to the surface. So CS is the surface layer derating factor, this constant, and this could be calculated with help of the this formula. Surface layer derating constant 1 minus 0.09, this much. So this value I'm just putting over here, CS, the same value, and the values, when we are putting the values in this, 1 minus rho 100 divided by 3000 divided by 2 HS is the, if you see HS is what we take. HS is what? Thickness of the surface material. And what thickness we generally we take? What thickness generally we take? What thickness we take generally? Usually, any substation guy, what thickness we take? Usually 100 mm, right now. We take 100 mm.
Yes.
Uh, 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 this thickness, right? So putting the value of HS as 1, HS as 1, HS as 1 over here, HS as 1 over here, HS is 1. So all the values we know now. 1 minus 300 divided by 3000 divided by 2 into 1. HS is this HS in mm or in meter. You check over here. In meter. So in meter it would be 0.1 only, right? 100 mm means 0.1. So 2 into 0.1 plus 0.009. Solve this value. The CS would become 0.70. This value. Now go in this formula and calculate the E step and E touch. E step and E touch, same as we have discussed here. E step and E touch. E step and E touch. This page number 27. This formula we have. E step calculate 1000 plus 6 into CS. 6 we have, CS we calculated 0.70. So 1000 plus 6 into 0.70 into 3000 bracket close 0.116 divided by under root of TS. TS would be your shock duration. So shock duration, what we take? There is two duration we take. One is the fault current duration. One is the shock duration. So when we decide the conductor size, in that case we go with the fault current duration, and that we take usually as per the equipment fault level, and that is 1 second. When it comes to the shock duration, so it is not because when any fault is happening, at the event of the fault, the CT will sense the fault, and it can sense in the millisecond. CT will give output to the relay. Relay operation time would be in the terms of the millisecond again, right? Relay will issue the tripping command to the circuit breaker, and circuit breaker will isolate into 50-60 millisecond as well. So the entire cycle will complete when any fault is happening in the range of something 200 to 300 millisecond. I mean,
Yes.
so but for the safety purpose, it could be the reason that if your main relay could not operate, in that case the backup relay will operate. So the backup relay again will have some delay. right? So in that case, in the TS soft resistance we take some margin, and usually instead of 300 millisecond, usually we go with the 500 millisecond. So TS would be 500 millisecond, or convert into second, that would be 0.5 second. So TS would be your 0.5 second soft duration. That if fault is happening, so on any person, the person will feel the shock uh, till 0.5 second. After, in that range, the fault would be clear by the breaker. So putting the values again in this formula, so TS would be under root of 0.5 seconds. Solve this value, is step and ETH, and then calculate the values, which is coming 2231.06 voltage and 680 voltage 0.06. And if you see, we haven't used any fault current here. No relation with the fault current, right?
Yes.
No, only I consider the soft duration and then surface flare resistivity value. Due to that purpose, if your swell is so this value is irrespective of the fault current, depend only on the swell surface flare resistivity, right, and the swell resistivity, because CS is depending on the swell resistivity. So this is, and this voltage, this step and touch voltage would be your tolerable voltage, right? Tolerable voltage right now.
Yes.
Tol Accept means how much voltage a person could tolerate without death. If I'm telling in a simple language,
Yes, sir.
this is tolerable current, and this is your tolerable voltage. 0.5 second is important here. Note down, right? And swell resistivity and surface layer resistivity is also important. Okay, means do not consider that I can withstand 630 voltage in your home also. You do not try to touch the current. That I can understand 630 voltage, so obviously 230 voltage and 400 voltage I can withstand. So do not attempt this kind of the things in your house. This is on some specific conditions, considering that this much resistance you have. So in your house, if you see that if you are standing on any wooden, what I can say, wooden bed, if you're touching the if you're touching the live fish, you don't feel the shock. Why? Because that wooden bed is providing the resistivity right now.
Yes, sir.
So that's why you are not feeling the shock. So similarly it is linked with the substation as well. Now so this much voltage you can withstand without death. Now coming to the criteria, basically this is step number 3, touch and step criteria. So coming on the step number 3, criteria. So what I mean by the criteria, in the criteria what I'm doing, that I'm comparing the voltage to voltage value. Thereafter, for the safe earthing design, in the event of the fault, when the fault current enters to the ground and ground potential increase, then we calculate how much the touch and step voltage developed. This space is too much important, so please concentrate. This space is going to set your entire calculations concept. So therefore, thereafter, the safe earthing design, in the event of the fault, when the fault current enter to the ground potential increase, then we calculate how much the touch and step voltage developed at event of fault. In this voltage, we haven't considered any fault current, right? Haven't we
Yes.
know any fault current. Now in the criteria we will consider if the fault current happening, so what the voltage developing, and after that we compare whether the developed touch and step voltage is below the tolerable or acceptable touch and voltage limits or not. If the developed touch and step voltage is less than tolerable touch and step voltage limit, then the person would be safe in the at the time of the fault with the provided earthing grid design. I will discuss here that part earthing grid design we will consider in the next slide. And if the developed touch and step voltage is not less than the tolerable touch and step voltage, then the person would not be safe. Earthing needs to be modified in order to get the person safe. And this evaluation is called the touch and step criteria. I hope I am clear with the statement with the step number 1, 2, and 3 so far?
Yes.
Yes, sir.
Step 4, 5, I haven't discussed, but step 1 to 3 I have discussed so far.
Yes, sir.
Okay, so what I do that because step 4 to 12 again going to take another 4, 5, 6 hours, so I could not be able to complete all this stuff today. So and I know that 2 hours is enough to adopt all the things. So please adopt all these things. Please like go through all these things one more times, right? And yeah, in the initial designing we will discuss all these things in the tomorrow sessions. Okay, and then further steps we'll discuss tomorrow. First we will understand about the steps here, and then we will perform the calculation one by one. So far we have discussed the 3 steps of the earthing calculations. Go through tomorrow remaining steps we will complete. Okay. In the steps initial designing, we will do the initial designing, then grid resistance calculations. We will do that. What should be the grid resistance, grid current calculations. These are the steps one by one we will discuss tomorrow. So, any query regarding to step 1 to step 3? Any query regarding this step? So, what we discussed, let us conclude what we discussed. We discussed that what is the objective. We discussed about that what kind of electrical earthing system we do in case of the substation. We discussed that we make a grid and depth of the grid is 0. Is the in the range of 0.5 meter to 1 meter depth that we take. We discussed that who will make this grid. So we discussed that civil contractor will make that grid, and that civil contractor will leave the earthing tails, and that earthing tail will be connected to the equipment metallic structure by the electrical contractor, right? And this is some kind of the site photo that here this rod diameter we have calculated right now, this rod diameter, and this earthing strip size also we have calculated, right? So here we see, then we started the earthing calculations. We have seen that we will follow the figure 33, page number 92, and based on that we will do the earthing system. In step 1 we discuss in this step 1 field data. So in the field data we discuss here and how to calculate the field data, and if in case your site is not completed, so
Your voice is not coming. Okay.
that would be your issue. Okay. Yeah, here we take the ERT report,
Okay. Now,
and then here we discuss about the concept about the short circuit current, this concept, and then here we discuss about the conductor size. So today agenda, in the today's sessions we discuss major one topic, what should be the earthing conductor size, right? This point I hope it is clear to all. And after that, we discuss about the touch and step criteria only. Criteria.
Sir, how surface regulating factor is acting in touch and step potential?
We'll discuss tomorrow. Yeah, we'll discuss tomorrow.
Yes, yes.
Don't worry. We have the touch and step potentials we have not covered. So we'll
सर
discuss.
एक चीज मुझे पूछना था हम लोग यहाँ पे डिपेंड अपॉन जो टाइम है टाइम ड्यूरेशन 0.5 सेकंड उसके हिसाब से मैंने निकाल लिया कि कितना मेरा टच और स्टेप पोटेंशियल होना चाहिए
हाँ?
तो अब ये निकल गया अब एक्चुअल साइट में मेरा क्या हो रहा है उससे ज्यादा हो रहा है कम हो रहा है वो फिर से निकालना पड़ेगा क्या
Yes. So actual at the event of the fault, so you calculated one touch and step potential based on your soil resistivity. That is right.
यस
And which is this value? Which is this value? One second. Which is this?
वो
Value?
8
Which is this value, right?
yes
And now again you have to recalculate that at event of fault. Okay. At the event of the fault, when the person is walking in the substation compound, and if the person is touching any grounded structure, so what voltage will develop between the grounded structure and the person, and between the two steps of the person, what voltage is developing, and whether the developed voltage is lower than this limit or not.
yes
This is your maximum limit that you can withstand, right?
अब इसको भी मैं मैनिपुलेट कर सकता हूँ सर डिपेंड अपॉन द टाइमिंग
Yeah, you can do. Yes, you can do depending upon the timing, depending upon the soil resistivity, depending
Yes.
upon your surface layer resistivity. That
Yeah.
will change.
Thank you, sir.
That will change.
Thank you.
Yeah. So tomorrow we will do, and we will change the values. We will change the CS and TS. Then we can see this value will change.
सर एक छोटा सा क्वेश्चन
Yeah.
सर ये ग्राउंड रेजिस्टिविटी का वेरिएशन हमें पता नहीं तो ये पोटेंशियल डिफरेंस कैसे निकलता है थोड़ा डिफिकल्ट है अंडरस्टैंड
Yeah. Come again, Jignesh.
ये ग्राउंड ग्राउंड रेजिस्टिविटी का डिफरेंस यानी वेरिएशन कितना होता है वो हमें पता नहीं है ना सर एक्चुअली हम लोग तो फ्यू पॉइंट्स पे मेजर करते हैं तो
So
ये
so
पोटेंशियल डिफरेंस कैसे
so
निकलता है
what we are doing that whatever we are doing for the few points, so that points average value we are selecting.
हाँ
You
दैट्स ओके वो पता चल गया
yes. So actual based on the average value we are deciding.
हाँ
It
तो वो
could be
सिंगल
the
वैल्यू
case.
वाला
It could be the case. It could be the case when the fault happening at each piece of the land. There could be different value. There could be different value.
ये हमें पोटेंशियल डिफरेंस मिलता क्यों है बिकॉज ऑफ रेजिस्टिविटी डिफरेंस ना सर
Yeah, because soil, each piece of land have the different resistivity.
हाँ तो वो हमें एक्चुअली पता नहीं है ना सर हम तो एवरेज वैल्यू एक ही लेते हैं
So,
सभी वैल्यू का
this is the approach that we follow, Jignesh, because we can't do the earth resistivity of the entire piece of the soil. Can you
ओके
do? Can you do like that?
वो तो नहीं कर सकते
It is not practically possible right now. You can't do that.
ओके ओके दैट इज अंडरस्टूड
Yeah. So what is the approach then? You do testing at least 4, 5, 6 places, right? Calculate the soil resistivity, and then you take and again you there is two value coming, the maximum value and the minimum value. So again we are taking the average, and then we are taking the overall average, and this value we are taking, and due to that purpose, Jignesh, what we are doing when we are calculating the earthing resistivity, so we do not keep the value neck to neck, means the RG value acceptable, the grid resistance value acceptable is 1 ohm, but we do not keep at zero point 0.9 ohm or 0.95 ohm. Even though 1 ohm is acceptable, we keep below safe margin, like we keep in the range of 0.6 to 0.7 or 8 ohm, because we know that there could be case that we are not taking the 100% identical resistivity of each piece of the land. So we do not, we in the calculus we also keep consider those margins. Is that clear?
No, we have to reach the standard. Let me go through the standard.
No, you ask me. I am the person here. I know the 200 page, not total overall. You put the query, I will give you the solution. If you have the time, you go through 200 page. I don't have any concern. I will share you.
I mean, I'm not in the position to put the things in the right words so that you can give me because I am doubting upon myself. कि मैं
Oh,
समझ
no
नहीं
worries.
पा
So
रहा
you go through that repeatedly. That would be the best way. Okay.
हेलो
Yeah.
सर, मेरा क्वेश्चन है सर इसके रिगार्डिंग ये जो 33 एंड 11 केवी सब स्टेशन के लिए बोथ के लिए ये कैलकुलेशंस वैलिड है दोनों के लिए?
It's valid.
Sir, this calculation we have done for the 33 kV and above substations, no? Or this is valid for 11 kV and 33 kV
Yeah.
also.
11 kV and 33 kV also. In this voltage, 132 by 33 kV we have considered. So 33 kV also coming in this substation.
And for AIS and GIS also, sir.
Yes, for the AS and GIS also.
And so my second question is, if we have the number of earthings, we require the number of earthings for the substation, sir.
Mm-hmm.
For GIS, sir.
Mm-hmm.
So we can make the means 4 to 5 earths, and we make we around the perimeter we laid the GI strips, sir.
Yes, yes.
So we calculate can we connect all the equipments from the same grid, sir?
So what we do, like in the pyramid in the like around your control building, around your building, JS building, you are making one loop of the earthing strip, right?
Yes, sir.
So
Yes, sir.
so do not, so in that earthing strip, earthing loop, you connect whatever the equipment we have placed inside the building. So those from those equipment you take the strip out, and that you connect with that earthing loop.
Okay, sir.
Yes, and usually on each corner of the building we provide the rod electrode as well.
And sir, neutral also transformer
Yeah,
neutral we can
for each neutral,
connect
yes,
from
yes,
the
for
same, sir.
yeah, for the each neutral as well. I have one video for the neutral. I can show you, just for your reference, just for the reference. So one second. Transformer neutral earthing, and here we have two welding winding for the transformer. So yeah, so could you see here this Vinas, here we have the trafo, and here we this is star still star star. Both side we have the star. So in that case, both side we have the neutral, right?
Sir.
So if you have delta star, so you will have only one neutral
Yes,
bushing,
sir.
right? So I'm taking this bushing, neutral bushing out, and from that I'm taking two conductor coming down, and for the to isolate with that main tank we have used here the insulators, okay, on each 670. 2 LV, uh, 2 LV neutral, and for each neutral two earthing pit. So
Neutral earthing is isolated one from grid earthing.
no, not isolated. And then I'll show you. I'll show you. So here two earthing is coming, and now this is the like your trapo, and now I'm taking out here. I'm taking out this earthing, and it is going to one earthing pit. This is one earthing pit. This is the gravel that we are discussing. This gravel.
Yes, sir.
This gravel. Which is going. This gravel. Yeah. So one pit here, and the next pit over here, and here we have this here. So in the last class, I have told you that when we do the earthing, neutral earthing, so we use the pipe electrode for the
Yes,
treated
sir.
earthing pit,
Yes.
and in that hole, because this is case of the solar, so we couldn't put water level manually each and every time in the summer season. So for that we have used this water tap. So I can just open, and then here we can put the water. Okay. So now this is the earthing pipe electrode coming, and thus this strip I'm taking, and then connecting this earthing bit.
So neutral earthing is separate than the base earthing, or
I think
it should be.
let me see. Could you see 1 second? So one pit over here, one pit over here. I just wanted to show you some. Uh, 1 second, 1 second. Please mute. Jignesh, from your side, I'm getting the background noise. Please mute yourself.
Sometimes it is suggested that you should keep this neutral earthing separate, other than the base earthing. So
Okay, okay, but it could be the some specific case of the project, but usually we connect this earthing pit with the mesh earthing as well. I will uh, share you some I will show you some drawing as well tomorrow in the class for the equipment earthing. You can see over
okay.
Sir, where we do the chemical earthing, sir?
there. See, at this place also you can do the chemical earthing.
So, chemical earthing is costly, sir.
Yes,
So
yes, it is costly.
why we switch on the chemical earthing, sir?
What happens that if in case your area is less, you could not get the lower resistivity from the conventional salt and charcoal earthing. In that
Okay, sir.
case, in that case, uh, we can switch from conventional earthing to the chemical earthing. In that we use the chemical bag, something 25 kg, and that chemicals we are like putting in that bore. so that we
So, sir,
could so that we could
where the
get
rock?
so that we could get the lower value of the each earthing pit resistivity. So if in case your area is not too large, cannot use too many conventional earthing. So in order to minimize the number of conventional earthing pit, we can switch to the conventional chemical earthing.
And if the soil is a rocky, sir,
Yeah, in
so
that
we
case
can
also.
prefer.
Yeah, in that case also very further
Yeah.
chemical earthing, so that we could minimize the individual pit resistivity.
Okay.
Yeah, okay. So this is the is site video.
Sir, for case of GIS, what is the area of earthing mat we have to, children we have to consider?
Santosh,
Yeah,
yeah, Santosh. So please go through the module number 5. In five we have discussed the GIS earthing. So please once go through, and if after that, if you have any query, you stay in the class 1 to 1. We can discuss with you.
okay, okay, okay.
Sir, for our substation actually we designed for like resistivity point 1 amps, giving particular etiquettes and these things. When after laying this grid, then we are checking the resistivity. It is already showing point 0.1 ohms without having the pit also.
Okay.
So is it now recommended to do the pit or it is not required?
Ah.
Because already the grid is having the resistivity
Yes.
less.
In that case only you can consider the pit for the surge arrestor and the CVT. Okay, high frequency earthing. Observe.
Surge arrestor is compulsory, sir. Pit, you, even
Yeah.
though the resistivity is
Not the pit,
0.1.
not the pit. You would consider the rod electrode as least, because you are getting the high frequency signal. So it is not recommended to discharge the high frequency signal into the common earthing grid. So at least you consider the rod for each surge arrestor and the CVTs. Okay, and
Then that one will be connected to the grid, sir, or it will be isolated
yeah,
from the
it will
grid.
be connected to the grid. It will be,
Okay.
yes. So the entire resistivity also could be minimized.
Okay.
Sir, in some you have mentioned there is a limit of 0.5 to 1 meter depth for spreading the earth mat.
It is not
There is
limited. It
specific
is the
reason,
it is the range, Santosh. It is the range.
range. So whether there is a specific reason for the selecting the range
I will
between
discuss.
point
Yes,
0.5 and
yes.
1
I will
meter.
discuss tomorrow. I have not discussed about the grid resistivity and this
Okay,
grid. That I will discuss tomorrow.
okay. Thank you.
Yeah. Okay. So we close for today, and the remaining portion of the earthing calculations will finish by tomorrow session. Okay. Okay. And whatever the queries that I couldn't read in your chat, I that let us discuss tomorrow again. Yeah. Thank you, Santosh, for your nice words. Thank you. Thank you, Avinash.